and welcome to today's Chai and Why. We are on the premises of Ruparel College in Mumbai, and today for our Chai and Why we have a very special visitor, Dr. Laurenz Widhalm from the Institute of High Energy Physics in the Austrian Academy of Sciences in Vienna. Laurenz, what is it that you are going to tell us today?
Yes, my talk is about something which turned out to be very fundamental in our understanding of the universe. It's about symmetries. Symmetries turn out to be important for conservation laws like conservation of energy or momentum, but it's also important that symmetries are not always perfect. We need a violation of symmetry to understand why our universe exists at all. And if we come to the most modern topics, it's also about the search for the Higgs particle. This is related to symmetry breaking. And the most general symmetries of all, it's called the supersymmetry. And this might be connected to the dark matter, which is out there in the universe, and we don't know what it is.
Laurenz is also directly involved in some of the experiments that study the symmetries and the breaking. Laurenz, could you tell us about the experiment that you are involved in?
Yes, I'm involved in the Bell experiment. That's an experiment in Japan. There is a particle accelerator near Tokyo called the KKB. We produce a lot of B mesons there, particles made of B quarks, and there we can study just these violations of symmetries I've been talking about before. So we could prove that a theory of symmetry breaking of two Japanese people was right, and they got the Nobel Prize just a couple of years ago.
The topic of my talk, of course, is particle physics, but there are different approaches if you talk about this topic. And I chose one which doesn't start telling you what particles there are or forces. I will talk about a much more fundamental thing, but which turns out to be essential for our understanding of the universe, and it's symmetries. And I think you all know examples of symmetries. I don't know if you have any snow here in Mumbai. In Austria we have a lot of snow, and if you look at snowflakes, they have a six-fold symmetry. And if you look at crystals, they also have symmetric structures. So, but what's the reason for this symmetry? I'm sure you know, if you look into the things, into the microcosm, you see that the water molecule is shaped in a special form, and that's the reason for the symmetry of the snowflake. And in case of crystals, there's a crystal lattice. So you see that symmetries, which are very small things in the microcosm, show up in our daily life, in macrocosm. And there are more examples. So what's the cause of this symmetry? So essentially it's coded in the genes, in the genetic programs of these plants and animals. So symmetry is something which is very common in nature, but also humans have a tendency to symmetry. This could be in architecture, for instance, but also in art. So somehow we feel that symmetries are beautiful. We like symmetries. And eventually, also particle detectors are built symmetrically. So if I now try to explain to you what symmetries are in a physics sense, I have to get a bit more technical, but I will give you some, I hope, clear examples. So let's look at the butterfly again. And if we are talking about symmetries in physics, we need to have define some symmetry transformation. This is just like a recipe to say what I have to do. And this recipe could be mirror all points at the line. So I could put a line here and just mirror all points of this image at this line. And what I get if I overlay the two pictures is something which doesn't look like a butterfly anymore. So you see I haven't chosen this line very wisely. So if I do it like this, there is no symmetry. But if I choose another line here, that's the line of symmetry of the butterfly. And if I try to put this in an equation, how can I put this into an equation? So if I write this more formally, I can say, well, let's say the symmetry transformation is called S1, and S1 applied on W, this is the original image, this gives some W prime. And what does it mean if I have a symmetry? It means that if I apply a symmetry transformation on something, the thing remains unchanged. What I get after mirroring the butterfly is a butterfly again. This is what this equation says. One more example. You think about the crystals I told you before. There's some crystal lattice here. And instead of mirror something, I can also move something. I can move it this way, or I can move it this way. And you can imagine if I do it, and I do it just the right amount, then what I will get is just the same lattice as before. So this again is a symmetry. Of course, if I move it only halfway or move it diagonally, then it wouldn't work. Then it wouldn't be a symmetry. But I have to choose the right vectors. So now what kind of symmetries do we have in physics? First we have symmetries called discrete symmetries. Discrete means that these are symmetry transformation you can either do or don't do. You can't do it halfway. And what we do, instead of the mirroring, we do something more general. We call it parity transformation. And this means we don't just have like a mirror, a plane, because then it would depend where I place the mirror, but I mirror at the origin. This means if I put it in a formula, that it just x gets to minus x, y to minus y. So, and you see here, this is an example. So this is the parity transformed image of this. And as you see, that's not what you would see in a mirror. But it's something you would see in a mirror if you do a mirror image and do a rotation. So what we do is we just put it in two parts. We have the parity transformation, and then by rotating we can define where the mirror is. One more discrete symmetry transformation is time inversion. This just means like playing a movie backwards. You all know that usually if you play a movie backwards, then it looks funny. It doesn't look like something which happens in nature. But if you look at the fundamental laws of mechanics, for instance, they are time symmetric. For instance, if you look at the game of billiard, if you just look the balls moving, just the balls, not outside, and you play the movie backwards, then it looks like it could happen both ways. Okay, this means just taking a minus sign to the time. So, and you're also coming to particles. There you can also do a symmetry transformation there. Maybe you have heard about antimatter. So for each particle, there's also like a mirror particle, which is called antiparticle. And these particles have the same mass, but the opposite charge and also opposite other properties. And this symmetry transformation just converts a particle to an antiparticle and vice versa. Okay, and usually we put a bar above the letter to indicate that we're talking about antiparticles. So for instance, this would turn an electron to a positron, which is the antiparticle for the electron. Okay, so far for the discrete symmetries, but there are also continuous one. Continuous means that you can do it in arbitrarily small steps. If you want to mirror something, you can just either mirror it or not. But if you do a shift, for instance, a shift in time, you can shift 1 second, 1,000th of a second, and you can do it as small as you want. Well, this is just a fancy way of writing this transformation. You don't have to worry about it if you don't understand it. I just like this notation. Maybe some of you who study math know it already. Of course, you can not only shift in time, you can also shift in space. This is also continuously, of course. And you can do rotations. You can change orientation just in space, any angles. Okay. And finally, this is a bit more abstract, but it will show you that this is really relevant. That's why I tell you it here. You can not only do what are called auto-transformations. These are transformations of coordinates. You can also do transformations. Particles in physics are described by fields. And this field is normally, we just call it psi, like here. And this field is usually something like a complex number. I don't know, maybe the younger ones of you don't know what complex numbers are, but just think of it as normal numbers if you don't know. And the point is, this number, this has some absolute value. This is the length of this arrow here. And some angle, some phase. This is just the angle from here to here. And what I now can do is I can keep the length of the arrow. I can keep the same, so the strength of the field will be the same, but I can change the phase, the angle. I can rotate it here. And this is what's called a phase transformation. Or mathematical name for it is U1 transformation. So I turn the phase. Now it's working. I hope you understand me better now. So I can turn the phase, and this, of course, is also one possible symmetry transformation. So, but I was telling you so much about symmetry transformations and symmetries, and maybe you wonder, well, why should we care? Maybe there's mirror symmetry or time symmetry, but is it of any importance? And this is why it is of very, very big importance, because this very clever lady here, Noether, found a theorem. It's called after her, Noether theorem. And this theorem says, if you have some theory, it can be as complicated or as simple or whatever, you have some theory, some physics laws, you apply a symmetry transformation. And after the symmetry transformation, you end up with the very same equations, very same formulae. Then you have a symmetry in these physics laws. And if you have this symmetry, then this theorem tells you how you can calculate something from these equations. From these equations, you get another equation. And if you calculate that, you get a quantity which doesn't change in time. It always stays the same value. And this doesn't depend on how complicated things are happening. So maybe later we'll have a cup of chai. And in a cup of chai, there are a septillion of particles. And imagine you have some equations and you try to calculate the movement of all these particles. So it's hopeless. But if I know such a conserved quantity, I can just calculate it once. And for all the time, for forever, I can say it will stay the same. And I can, this will help me to know if what things can happen to this system or what cannot happen. And I'm sure you all know the examples I will show you now. So the first example is conservation of energy. Well, maybe you learned at school energy is conserved. Well, that's it. But why? Chai and why? We are asking why today. You can just believe it, but you can also try to find a deeper reason for it. And the deeper reason is a symmetry. It isn't the case that this famous equation changes from day to day. It's just E equals mc squared every day. Today, tomorrow, the day after tomorrow. So law of physics do not change with time. But that's a symmetry. The symmetry, that's a symmetry with respect to a shift in time. And this symmetry of my theory gives me a conserved quantity. And this turns out to be energy. So if you ever wondered why is energy just calculated that way with this formula, you can just calculate it from this symmetry and the Noether theorem. The physics laws here in Mumbai are the same as in Austria. It's a symmetry in space, and this gives you a conservation of momentum. And here, symmetry with respect to rotation. You can rotate, and the physics laws aren't different if I look this way or that way, and this gives you a conservation of angular momentum. And finally, if you wondered why I was telling you about this phase transformation, it turns out that this phase transformation, this U1, this is related to the conservation of electrical charge. So you see, everything which is conserved somehow is caused by some kind of symmetry. So this is just an overview, but let's go on. Symmetries need not be perfect. Example of the butterfly, this wasn't a perfect symmetry. If I look very closely, it's not perfectly symmetric. Or phases are not perfectly symmetric. So is physics perfectly symmetric? Well, in daily life, things obviously are not. But what about the fundamental laws of physics? And we already talked about the continuous symmetries. So there we have perfect symmetry. So tomorrow the laws are exactly the same as today, not just somehow. But what about the discrete symmetries? I thought about this parity, time inversion, charge conjugation. And at first it seemed that this all is perfect. But then in the 50s, there was a famous experiment done by this lady, and she found out, she did some experiments of radioactive beta decay of cobalt atoms, and she found out that, just imagine, she had some set of an experiment. You can look, you can put a mirror and look in the mirror what happens. And then you can do the experiment again, just all mirrored. And usually what would you expect is if you just do a mirror setup, that what will happen is the same as you have observed in the mirror before. But actually it's different, it's just opposite. So what you see in the mirror of the first experiment cannot happen in nature. And that's why we say nature is not mirror symmetric. The parity symmetry is violated. Let's now just mirror the experiment, not just to parity, but also to charge conjugation. Make a mirror experiment and make it out of antimatter. Of course, you cannot do that in practice, but you can think about it. And in principle, it seemed that then it should be symmetric if you do both. It's called CP, charge and parity. But then in 1964, there was another experiment with kaons, and they found, again, that something was happening that shouldn't happen if CP is a symmetry, if CP is conserved. But in this case, it was only a small violation. So you see in 99.8 of the cases, the thing that happened, it was just what was expected, but in 0.2%, something different happened. So there can be violations which are small, but nonetheless important. Again, there was a Nobel Prize because under Sakharov, he was thinking about a very fundamental question. Because if you think about, okay, there is matter, there's also antimatter. I told you they are somehow symmetric. And if you look back to Big Bang, when the universe was created, there should be the same amount of matter and antimatter. We cannot think of a reason why there should be a different amount. If it's perfectly symmetric, if the laws are symmetric, if there's any process which generates matter, there has to be as much antimatter. But obviously our universe is filled with almost completely only matter. And there are only very small amounts of antimatter in nature. So what's the reason of this asymmetry? And he thought about the conditions, and he found that one of the conditions to have this matter-antimatter antisymmetry is this CP violation. So what we found in our experiments in 1964 actually was something very important for our existence at all. So again, an overview. You see the symmetries, and it turns out there's almost none of this is conserved in the universe, only if you compare all three, charge, parity, and time reversal, then, to our knowledge, it's conserved. Now I'm coming to another topic. Symmetries can not only are important for conserved quantities or existence of the universe, they are also very important to understand forces. So what do I mean by that? First, I told you I can do this U1 transformation, this phase transformation. But this means I change this phase, this angle of the field, globally. In the whole universe, I do the same transformation. The idea is now, so common sense tells us if I have a particle here, then the phase of something on the other end of the galaxy shouldn't matter much. So what if I assume that I can change this phase in different points in space differently? So now I have a different phase at each point in the universe. This is called a local transformation. And maybe this seems to be too much. Well, I can change at every point. I can change any phase I like. So can this be a symmetry? So I can try. I can look at my equations. And if I just have the equations for a particle field like electron, then it turns out it's not invariant. But if I think that particles are interacting with each other, if I include the electromagnetic interaction, then I find that the theory is symmetric. Although I can choose the phase at each point just arbitrarily. And this really seems like magic, because this just works because the laws of electromagnetism just are as they are. Maybe you have seen my T-shirt. So here are the Maxwell equations. So these are the equations telling about electric forces, magnetic forces, and how they interact with each other. Also electromagnetic waves, everything. And you see these equations are very special. They're just not arbitrary. They just look in a special way. And it turns out that they are just that way that this symmetry is realized. So one could wonder, is this coincidence or is this a deeper truth? And we today think it's a deeper truth. So we now put it the other way around. So we say if we found a symmetry, a global symmetry, then we say, well, let's assume it's also a local symmetry. And this results in some kind of interaction. And interaction also comes with force particles, like the photon for U1. That's photon is the carrier of the electromagnetic force. So each local symmetry generates an interaction between particles and generates corresponding force particles. I'll give you one example of an application of this. If you look at quarks here, we know that inside the proton there are 3 quarks, and we know they cannot be all in the same state because of the Pauli principle. So there has to be some property which is different for the 3 quarks, and we call this property color. That's not a real color, but it's just to have an idea in mind. And so we have a red, green, and blue quark. And now we can look if there might be a symmetry. And let's assume that we don't have to use just these 3 colors, but assume we are allowed to mix it. I can mix these 3 colors to get a new red, and this to get a new green, and this to get a new blue. And mathematically, this is described by a matrix, or it's called SU3 because we have 3 times 3 quarks. And if we have the symmetry, and if we assume the symmetry also is valid locally, then we get a theory of a new kind of interaction. And this new kind of interaction is what's known as strong interaction, and I get new force particles, which are known as gluons. And because this is more complicated, I have 3 times 3, there's not only 1 gluon, there are 8 gluons in total. And the theory is known as quantum chromodynamics, and this force is responsible for the quarks staying together in the proton and neutron, and also for the nuclei to hold together. So you can say that this color symmetry is fundamental for the existence of atoms. Maybe you've heard about the Higgs particle. This is a particle we are trying to find at the LHC experiment, LHC accelerator. But what's the connection to symmetry? Well, the question is, what's the origin of mass? We know a lot of particles, and they all have different masses. So there doesn't seem to be any symmetry there. But in our fundamental theories, all particles from start are massless. They all have the same mass 0. So where does the mass come from? The idea is that there is a Higgs field, and this Higgs field has a very special, funny property. So normally, if a field gets stronger, then also the energy gets stronger. But in case of the Higgs field, you see, if the Higgs field gets stronger, the energy gets less. And only at some point, it gets bigger again. So what is the consequence of this? So in principle, this is, of course, symmetric. And if you have a very hot universe just after Big Bang, you are somewhere up there, then you don't see this down there. You don't see the difference. So particles are in principle massless. But what happens if the universe cools down? And you see at some point, when the energy falls below that point, the universe has to decide to go on this side or go on this side. And this is what's called symmetry breaking, or spontaneous symmetry breaking, because it happens just at one point in time. And the universe has to decide, well, I end up at a state here where I have a non-zero Higgs field. So when the universe, normally when something cools down, at the end the fields are 0. Energy is 0 or almost 0, and the field is 0. But here you see the universe has some Higgs field. And this is really about the whole universe. Imagine the whole universe filled with the Higgs field, and all the particles have to move through this Higgs field. And you can imagine, I cannot explain you in detail theoretically, but I think you can imagine that by moving through this Higgs field, particles somehow interact with that, and they get their mass by this interaction. So this sounds maybe interesting, but there's one flaw. We don't know if this is true. The point is, we are just now trying to find out if there is really a Higgs field. And we are doing that by trying to produce waves in this Higgs field, excitations of this Higgs field. Excitations in the Higgs field, that's the Higgs particles. If it manage to produce a Higgs particle at LHC, then we have proven that there is really a Higgs field. And another thing is, this comes from cosmology. This is so-called dark matter. If you try to understand the rotation of galaxies, why galaxies hold together while they rotate, we find that there has to be much more matter than what we usually know and see. It's called dark matter. And we also see dark matter by this gravitational lensing effect. This is because light, if it passes by a large mass, a part of light is bent. And from there I can calculate the amount of mass here. And here's the famous image of the bullet cluster. So what you see in blue here, that's dark matter. And here it's also an image, if you look into space the bright spots here. These are the galaxies. And the blobs here, this is all dark matter. And what we also see from this picture is that compared to ordinary matter, there is much more dark matter. It's 6 times more dark matter than normal matter. What's the flaw here? We have no idea what this is. Well, we have some ideas, theoretical ideas, but they have to be proven experimentally. And again, it's related to some symmetry. And in this case, it's even a supersymmetry. So it's the most general symmetry we can have in a particle field theory. It's a symmetry between matter and forces, between matter particles and force particles. So imagine for each particle, for instance, for the electron, there's a supersymmetric particle called S electron, supersymmetric electron, and this would be a force particle. Or I can have the gluon as force particle, and then have the gluino, which is a supersymmetric matter particle. So, but what about the supersymmetric particles? The fact is we haven't seen any of it. So we assume with the symmetry that there are twice as much particles as we know yet. So maybe that's expected too much, but there are several theoretical reasons to believe in that, because it solves a lot of problems we have with our theories, and it could be the explanation for dark matter. Because if there is some supersymmetric particles, there has to be some, well, the heavy ones can decay, but the lightest supersymmetric particle cannot decay in anything lighter, so it has to remain. And this could be the source of the dark matter. So is there a Higgs? Does SUSY exist? We do not know yet, but how can we know? Well, we are in a fortunate position just right now that we have a very nice device which will help us to find out. That's the LHC, the largest machine in the world, the biggest particle accelerator, and here we can collide particles and try to have conditions just like we had just after Big Bang. And under these conditions, we hope to produce Higgs bosons if they exist, SUSY particles if they exist, and to give you some impression of how this machine looks like and the experiments. Maybe in 1 or 2 years, I or somebody else can tell you, yes, we found the Higgs, or yes, we found the SUSY particles. Thanks for your attention.